let's start with my presentation, handling billions of edges inside a graph database. A little bit about me. My name is Michael. I'm part of the ArangoDB core team, so I'm co-committed at this open source project, and I'm especially responsible for everything that has to do with graphs in our database, which means the graph visualization was intended by me, all the graph features that we have, and the new feature, which is called Smart Graph, that will be covered in this talk. In my free time, I'm hosting a meetup in Cologne, which is Cologne.js, and I'm holding a master's degree from RWTH Aachen in Germany. Good, but now starting with the topic. What are graph databases? As most of you didn't show that they are already using them, I'll do a short introduction. So, typically, graph databases store schema-free objects, which are called nodes or vertices, plus relations between them. So pretty much the same thing as you know from a relational world. You have a table containing all the vertices, plus a many-to-many relation containing all the edges. But graph databases are a bit more special. They are specialized on all queries that are really focusing on these relations and having relations inside, having information inside the relations. So in most graph databases, the vertices are schema-free. That means you do not say every vertex has a name and age, and this age has to be an integer and isn't allowed to be null or something. It's just you have a JSON object and you drop it inside the database and it stores it. So that means whenever your data format changes, you do not have to migrate the database. You just have to insert the new format, and that's all about it. Then the edges, relations, always have a direction. So it is defined which vertex is the starting vertex and which one is the target vertex. In terms of querying, you can either query alongside this direction or reverse the direction or say, I don't care, go both directions. And depending on the technology you use, in many graph databases, the edges can also be arbitrarily complex. So that means we have nested objects inside the vertices and the edges if we want to. So edges can be queried in both directions, so taking the direction into account, going against it, or without caring for the direction. And the things where graph databases actually got a huge advantage above relational databases is if you do not know how many steps you want to go. So say I have a person A and a person B, and I just want to find how they are connected. I am personally not able to write that SQL statement to find out how many steps I need in between. And they have easy query mechanisms if you have a range of edges in between. So say I buy a ticket at a train station and I can go up to 6 steps. So 6 stations. If I do that in a relational world, I can store the data easily, okay, no problem. But if I want to query, I need one join for 1 step, another join for 2 steps, another join for 3 steps, another join for 4 steps, and so on and so on. And then a final join to just put everything together. Query looks pretty much like this. In a graph database, it's a one-liner. And what they also can do is shortest path between 2 vertices. Just say vertex A, vertex B, just give me the shortest connection. One-liner. So what are typical graph queries where they perform very, very good? Example, give me all the friends of Alice. That would be starting at one point, 1 step ahead, look at all the direct collected objects. Give me all friends of Alice. This is something special, so it's just 1 step plus an additional step, but please ignore all the direct friends of Alice in the result. Which means in the first step you collect all the friends, and then collect all the friends of French which are not in the first step. Given 2 people, what is the linking path between them? And I do not know how many steps are in between, or if there is actually a linking path. And the graph database can actually answer this query. Then the one that I already told you, which train stations can I reach if I'm allowed to drive a distance of at most 6 stations, switching trains as often as I like. But most queries are actually the so-called pattern matching. And the idea of pattern matching is that I describe the layout of a subgraph and I map this layout on my entire database and find all the parts of the graph that match to this pattern. So one example, give me all the users that share 2 hobbies with Alice. The pattern would be Alice, 2 relations to different hobbies, 2 relations to 1 user. Find me all users that actually match this pattern. And we can make it more complex. Give me all the products that at least one of my friends has bought, together with the products that I already own, because those are the products that I'm probably interested in. But please order them by how many friends are in between, and by their rating, but only the top 20, because that would be the slide you see below of Amazon. Please buy these products as well. What are non-typical graph queries? So queries where graph databases are really bad at. What they cannot do, or not really good, or not do in a good way, is something like queries only based on attributes, so not taking into account any relations. So give me all the users which have an age attribute between 21 and 35. Because that means the graph database has to do full collection scans, which is very expensive. Or give me the age distribution of all users, so taking all of them into account. Or just please give me the distinct names of users that I have in my database. And the reason is that in a graph database, the query mechanism that you use is a so-called traversal. And I like to explain this by using an example. And my example is that I want to iterate down 2 steps, 2 edges, plus I want to apply some filters onside these edges. And whenever I start a traversal, the first thing to do is I have to pick one starting point. In this case, I call it S for start. Then I take a look at S and find all the connected edges for S and all the vertices that are connected to these edges. Then I have to check and go through all these edges and check, okay, do they match my filtering conditions? And in this case, for example, the 1 to C does not match the filtering condition. So from now on, this part will be ignored, and those are still in the active records. And now I pick one of them, for example A, and I do the same thing again. So select all the edges going out of A, leading to D and E. So now I'm having the second step. Again, I apply my filters. This time I want to ignore D. And now I have found my first result. Going from S to A to E would fit the conditions that I have defined. So this is my first result. And now the traversal actually is standing at this E vertex. And it knows, okay, I'm now in depth 2. I don't have anything more to do. It goes back to A and check, is there any edge that I haven't processed yet? In this case, no, because I want to ignore D. So I go back to S and check, is there any edge that I haven't processed yet? And then yes, there is B. So I go from S to B and then do the same thing for B. For B, I find all the edges which are pointing to F. Go down there, apply the filters. In this case, it's okay. And now I got the second result. So this traversal gives me 2 results, SAE and SBF. And then again for F, I have to do the same thing. I'm on depth 2, so I don't have to do anything here. Go back to B, check if there is any edge that I haven't processed yet, and then go back to S. The traversal that I've just shown you, or the algorithm that I've just explained, is a so-called depth-first traversal, which just always goes down as long as it can, and then goes up again and tries to find other alternatives, and thereby creating the overall result. An alternative to it is a so-called breadth-first search. The breadth-first search works that it starts at the same point S, figures out A, B, and ignores C, but then the difference is it first computes all in depth 1, and then goes to depth 2. So in this case, it doesn't really matter, but assume that I would return A and B as proper results as well. Then it would mean that in the depth first, I would return SA and SAE and then SB. With the breadth first, I would return SA, then SB, because that's steps 1, and then SAE, and so on. And this is very important later on for performance. Now let's talk a bit about complexity, because that is the major difference of graph databases compared to relational databases. So, a graph database typically does not depend on the overall size of the edges that you store. It just depends on the result size. And that is because the complexity is computed as follows. You have to find the starting vertex, so the one point where you issue your traversal from. How fast you can find it depends on the index. Best case, you use a hash index for that, which has constant time lookup. If you don't have a hash index, it's simply a sorted index, so it's log n lookup time. And now comes the expensive part. For every depth, I have to compute 4 additional steps. First of all, I have to find all the connected edges. Therefore, I either use a hash-based edge index or so-called index-free adjacency, which means that the edges are stored directly next to the vertices. And therefore, in both cases, I can find all the list of edges that I have to process in constant time. And then the expensive part is I have to check if the edge matches. That means I have to take a look at all edges, one at a time, linear complexity. Then I have to find the connected vertices, because they are typically stored somewhere else. Again, I have to do this for every edge, linear, times the complexity that I need to find a vertex, using a hash index, constant time. And then I have to probably have defined filters based on the vertices. I have to, again, go through all the vertices, check if they match, again, linear complexity. But the 4 steps can be done in one go. So for every depth, I need 3 times n complexity. But the problem is, in the next depth, so depth 2, means I do not have 1 input, but I have 3 times n input. And that means 3 times n times 3 times n complexity for depth 2. And then depth 3, 3 times n times 3 times n times 3 times n, and so on. Linear sounds evil? Yes, it is. But it is not linear in the total amount of edges. So I can store billions of edges in the database. If my result just touches 24 of them, it's fast. If my result touches billions of edges, it's slow. And therefore, the traversals are solely scaled with the result size, and they are not affected by the total amount of data, because they don't care. They don't check for other edges. They have this edge index that directly points them to the right results. But you have to keep in mind that every depth increases the exponent. And there is a rule for so-called natural networks, so networks that have been created by your users, for example. So every social network or street networks or something, they're typically natural networks. And they have a phenomenon that is so-called the 7 degrees of separation. That means that it takes at most 7 steps to get from every point to every other point. I think with Facebook is even below that, but just pick 2 random people, let's say Barack Obama and me, and then find the linking path, and I'm pretty sure it's less than 7. Because there are those very important persons that have like millions of friends or followers or whatever, which just make very, very short connections. But in terms of querying, you have to make sure, okay, whenever I have to do a 70 depth traversal, then it's probably a better idea to just do a full collection scan of all the edges, because you will touch them all anyways. If you artificially create your graph data set, so by just splitting up some attributes and stuff, then this doesn't hold, because it's just for everything that is built naturally. Everything you do artificially, you can have further depths for searching, because then you have the amount of edges actually connected to one vertex under full control. So it's not that expensive then. So, now give me a chance to talk about my little child, the project that I'm working on. It's called OrangoDB. OrangoDB is a multi-model database which allows to store documents, graphs, and key-value pairs just in one technology with one query language called AQL to cover them all. So you can do document queries, graph queries, and joins, all of them combined in a single AQL statement, which gives you a lot of power. And also ArangoDB supports ACID, including multi-collection transactions, something that is missing in most of the document stores out there. And ArangoDB will be the technology that I use to show you how this actually works with the graph databases. Short introduction into AQL, because that is the language that we are going to use. Shortest AQL statement possible is for users in users. So for user in users, return this user, which is pretty similar to select star from users. Just in AQL, we are using these for loops. Who has done xquery, it looks pretty much the same. But the cool thing about AQL is you do not have to define which indexes should be used. Everything is figured out by the database itself. You can add filters. So I can just say, please only take into account users with the name of Alice. And then I can do, as I promised, some graph steps. So for product, in one outbound step, so I take into account the direction, starting at user, using the edge relation has bought, and then return the product. And what I will now get is this pattern. So I start at Alice, which is known. I know that the label or the collection here is has bought. And then I want to find everything that is bought by Alice. And I can make it very, very complex, which is the recommendation query again. So I'll start with recommendation. I can also get the last edge, and I can get the entire path in 3 steps. Any direction, so I do not care for the direction. Starting again at my user, and only using has bought relations. I can apply filters on the path or on recommendation or action as I would like. I can apply limits, and then I can return the recommendation. So what this does is it finds me someone in around my age who has bought the same product and suggests me everything that this guy has bought, which is less than 25 euros or something. Good. To show you that it actually works, let's start with a short demo. So this is web interface of ArangoDB. It shows you everything that you expect from a web interface. I have in my data set 2 collections, airports and flights, which are not that large because that data set is running on my local machine. So it's the whole airport list of the United States. They have around 3,400 airports. And I have an edge collection which connects these airports, called flights, which are, I think, 2 or 3 months of domestic flights between these airports. And this is 1 million of these flights. I've reduced this data set because it contains, the original data set contains, I think, 12 years of all the domestic flights in the US, and that is too large for my machine. Good, and now let's issue some queries on it. So simplest query is for airport, in airports, return airport. So this would give me a select star of airports, execute, and here we go. Let's apply some filters. Filter airport._key, which is a unique identifier in ArangoDB, is equal to SFO, which is San Francisco. And now I will just find the San Francisco airport. But I'm not interested in the airport. I just want to go from San Francisco to somewhere. Yes, I can actually do that. So there is a function for that, which is, I think it's called like, where I can just give a pattern like this, San Francisco. And I think it has to be airport.name. So I could do something like this. I don't have the airport name in them. I won't try it out right now because I'm not 100% sure of the syntax. But yes, I can do that, which will just check if in this name attribute there somewhere is the term San Francisco. Good. Let's just return to this version. Good. And now let's figure out where can I actually go. So just one step. So for target, in one outbound, starting in San Francisco, using flights. And as the dataset contains all flights a day, and from San Francisco there are multiple flights to the same airport on the same day, I just want to make sure that I just have a distinct set of targets. And off we go. I get 64 different airports that I can fly to starting in San Francisco. Direct flights. Good. But now let's talk a bit about the problems that you have with graph databases. So first of all, you remember the complexity. It scales to the power of depths. 3 times n power of depths. Because the filtering of non-matching edges is linear. And then we have a problem with natural graphs that there are typically so-called supernodes. Supernodes are those nodes, like Barack Obama, who are connected to millions of other people. And whenever you have to traverse over them, that means you have to check all the million just to throw away most of them. And that is extremely expensive, and that increases the complexity of a query. And what helps there are so-called vertex-centric indices. Vertex-centric indices allow you to index all the edges connected to a vertex based on the vertex plus an arbitrary number of other attributes. So that means if I, for example, only want the newest 100 followers of Barack Obama, I can just index Barack Obama or the vertex identifier plus the timestamp, and then I get a sorted index on these attributes, and I can easily find the first 100 ones. So I can find the initial set of edges in identical time than I can do with a typical edge index. But I do not have so many post-filtering to do, because the index already covers it for me. And this decreases the n, and therefore the overall complexity. So in the example, first one, I just start at v, and I have to check all the 8 edges. If I would now use a vertex-centric index based on v and the color, I would easily figure out that there are only 2 green edges pointing out of v. So now let's take a look how this actually works and how this speeds up the whole process. Now let's plan our flights starting in San Francisco. And I would like to figure out where I can go in 2 steps. But when I fly, I do not want to wait a week or so to get my connection flight. I please want to fly on the same date. So therefore I just apply some filters. And the first filter I want to apply is path.edges star, which means all the edges on my path .day should all be the 4th. No, I think it's day of month in this dataset. So day of month. That means I'm flying on the 4th of every month. So I probably have to wait 1 month to get my collection flight, which is bad. So again, filter path.edges star .month all equals 1. And that means I would just travel on the 1st of January starting in San Francisco. And let's figure out which targets I can reach. One thing here again, I would like to use a breadth first search here. Again, for performance. Because first I want to find all the distinct airports that I can reach in one step, having the same day and date, actually, and then go only from the distinct set 1 step ahead. Yes, the default is depth first because that internally needs less memory and less state to compute. And in most cases it is the one that you actually need. If you want to find everything and you do not care for the ordering or for filtering in between, then depth first is typically the one that you need. Breadth first is especially useful with the following additional command. It's called unique vertices global. And this actually changes the behavior of the traversal. that does a check whenever I go to a vertex and checks if it already has visited it. If yes, it just ignores it and goes to the next one. If not, it will continue here. So this means with this query now, I start in San Francisco, check all the distinct level 1 connections, and then the level 2 connections starting from there. And if it doesn't do this triangle flights, so starting from San Francisco going to whatever is connected, let's say JFK, and then from JFK to Denver, it doesn't check that against starting in San Francisco, going to Denver, and going to JFK. That would just be one of those passes would be taken into account now. Good. And now let's find out where I can go. And you see this query takes some time. Yes. So, but the thing is that with breadth first, I cannot use the unique vertices global because the result is not deterministic anymore. Because it then depends if I go 2 steps and go to Denver, and there is a different path in 1 step which goes to Denver. It really depends which one is taken first, if I continue flying from Denver or not. So if I first go the longer path, I would ignore that there is actually a shorter path. So I have to remove this one. And we can execute this, and wait, and wait, and wait, and yeah, wait some more time. Yes. Yes, so in this case, I really have some duplicated paths that I have to check. That's right. So that is why it takes so much more time. So this is 12 seconds. The other one was, I think, 1 second, if I'm not mistaken. That's, yeah, a little bit less than 2 seconds. You're right. Good. Now let's go back and I'll show you how vertex-centric indices help. So, because, as you can imagine, San Francisco is an airport where a lot of flights start at. So I have to check a lot of edges at San Francisco. And it probably leads to another vertex, another airport where a lot of flights are. So only thing I have to do is go to my collection, define an additional index. So right now I only have an edge index which is based on from and to, which is the one that is used right now. So I add an additional index, hash-based, because then it's constant time lookup, from, and I have used month, and I have used day of month on the edges. Create, and there we go. And here you already see the estimate for the edge index is pretty bad. Yeah, so this is the chance to find one specific edge when using this index. For the combined index, if I have all these 3 at hand, it's way higher. So the optimizer figures out that this index is better to use in certain cases. Which one? Yeah, so there, this means that I can drop this index again. I cannot drop the primary index and I cannot drop the edge index. So I can drop all my user-defined indices, but those are system indexes that cannot be dropped. Good. Go back to the query. Let's ignore this one. So 2 seconds to beat, and off we go. So it's just 46 milliseconds having the exactly same result. The ordering might be different, but the total result is identical. So vertex-centric indices will help whenever you have so-called supernodes, and you have certain criteria where you can actually beforehand reduce the set of edges, not during the checking. Yes, please. Again, please, I didn't get that. Yeah, so if you index everything, so the hash index that I used is only in memory, so that means all the indexes have to fit into memory, the hash-based ones. And if you have enough memory, you can do it. If you do not have enough memory, then you get into out-of-memory situations, which are bad. Yes, there is. So let me just check. Yeah, you have seen the journal size, which is some internal thing. There we go. So at this state, we have 3 indices, and they use up 230 megabyte of my RAM. Yeah, this just tells you some more important information. So whenever you're not sure what this actually means, the information. In terms of memory, yes, but right now at least in our database, it's not possible to say, okay, only this one is indexed, but that may be added in the future. But for sure, that's right. If you have just 4 edges for most of them and then 1 million for only one, then it's a good idea to just index the one. You're right. Good. Okay, so first performance boost done. But as I told you, this data set is only on my local machine. What if I have a graph that is large enough to do not fit on my machine? So, scaling. I have a graph that is so large that I need to store it on several servers. Vertex Centric's indices help with supernodes. They also help with distributed graph databases, but they do not solve the complete problem. So, the idea is to distribute the graph that I have on several machines, and the mechanism there, as you might know from other NoSQL databases, is called sharding. So I just chop my data set into parts and put each part on different machines. And I cannot put all the parts on one machine because otherwise I will not have this problem. So how to query it now? First of all, there's no chance that I get a global overview of the complete graph, because that would mean put the entire graph onto one machine. Doesn't fit. And what about edges between those servers? So those are the problems that we have to tackle. But first, let's start with this cluster thing, and there I would like to introduce you to a nice stack of features, and that is called Mesosphere. That's the company behind it. And they have 3 tools that they actually use to make working with a clustered environment very, very easy. So first of all, they have Apache Mesos, which is installed on every client machine, so every part of your cluster. It figures out how many available storage you have, how many CPUs you have, how many RAM you have, and so on and so on and so on. And they all talk to each other, and therefore they can provide a complete picture. Okay, your complete cluster has 200 terabyte of RAM in total. Then there is Marathon. Marathon sits on top of Mesos and talks to all these agents. And Marathon has the ability to start a process, just like you run on your PC. You click on an executable file and it runs it somewhere. And Marathon does the same thing, just for a cluster. The process says, I need 8 gigabit of RAM, 20 gigabit of disk space, and 2 CPUs. Marathon asks the Mesos agents, okay, who of you has this specification free? And then it spawns this process on this server. And the cool thing is, whenever this server dies, Marathon figures out, oh, there was this process running there, and just started somewhere else, without you doing anything. So it just heals your complete cluster without any interaction, which is pretty nice. And then we have DCOS on top of it, which gives you a nice app store and a nice monitoring tools and like some convenient UI to manage everything that is run through Marathon. And ArangoDB is actually in the DCOS app store, so you just go to the store and say, please install me ArangoDB, 5 instances, and off you go. You have a sharded instance of Arango. Is Mesosphere required? The answer is not, so ArangoDB can run clusters on its own, but you have to do some manual effort. There is a script which actually reduces this effort to writing one line of code on all the servers that want to play a role in the cluster. But you have to figure out the IP addresses and all this stuff yourself. So correct startup ordering is already done by our script. Then you get automatic failover. So whenever one of those machines dies, the replica set takes over. You can rebalance all the shards automatically and all the features that ArangoDB offers. What we only do with Mesos is a complete self-healing. So we do not figure out, oh, there is some other server running somewhere and just install ArangoDB on it to just connect it to our cluster because one machine went away. This does Mesos. And it also automatically restarts the ArangoDB whenever there has to be new machines added to the cluster. And if you do not use something like Mesosphere or Kubernetes, which is an alternative, we suggest that you have someone on call during night whenever there is a server down that you could fire up a new one just in case. Good, but now let's distribute the graph. So what are the dangers of sharding? So first of all, I have only parts of the graph on every machine. I do not have the complete graph in one place. This introduces the problem that neighboring vertices may be on different machines. And even worse, edges from these vertices could be on other machines as well. So for one neighbor, I could have the starting vertex here, the edge on that server, and the neighbor vertex on this server. Worst case. And therefore the queries need to be executed in a distributed way. They have to collect the data where it actually lives. And the results need to be merged locally. That means you cannot query, please give me the complete graph now, because that would kill your client. Graph is too large for it. But you can still query some parts of the graph which fit into your client. So what are the strategies to actually do some distribution of the data inside the cluster? The easiest one is a so-called random distribution. That means for every vertex and every edge I have, I throw a dice, and depending on the result, I put it on one server. Advantage, every server takes an equal portion of the data, so I have really an equal split of my data, total data amount on all the servers. It's super easy to realize on the database side. It doesn't require any knowledge of the data, it just always works. This is a huge advantage. But the disadvantage is, in most cases, the neighbors are on different machines. You do not have any knowledge that the neighbor is actually local or not. Probably the edges are on other machines than their vertices, even worse. And that means a lot of network overhead is required for querying. So that is the price you pay if you go for random distribution. Because if we do random distribution and we have the graph on the left-hand side and our 3 servers on the right-hand side, the graph looks like this. So you have no idea how it actually looks in original. No chance to recompute it by hand. But to show you it actually works, demo time, now I switch to different ArangoDB versions. So this one is now closed, and this is running in Cologne, where I come from, in our small data center consisting of 3 servers. I have in my cluster 3 coordinators and database servers. So in the ArangoDB philosophy, coordinators are the ones that the user talks to. You send queries to them, and they figure out where the data is. And database servers are responsible to actually take the data, store it, and deliver everything that is asked from the coordinators. So in total, I have 3 machines, each of them running 1 database server, 1 coordinator. I have inside this cluster imported a social network, which is called POCAC, and it is available from Stanford University just for free download. That is a bit anonymized, but a lot of data is still inside the social network. And I have imported it in 2 ways. So you see here profiles, profiles smart, relations and relations smart. Profiles and relations use the random distribution that I have just introduced. In total, I have 1.6 million profiles, and if I'm not mistaken, 30.5 million edges between those, split it on 3 different servers. Good. Now let's query those. Make it a bit more complex. Oh, I haven't introduced the graph keyword yet. So in ArangoDB, it's also possible to group several collections. So collections are these profiles, for example, and the relations into one graph. So whenever you have multiple relation types and you want to query all of them, you typically group them in a graph, and they belong to one another. And then you can just say, please query the entire graph. Or query only the relations, only whatever, the likes or the hates relation or whatever. And I have created two graphs, so PokeHack Random, which uses random distribution, and PokeHack Smart, which uses the smart graph distribution that we come to in a second. Good. Now let's execute the query. I start at a given profile, where I know actually the key address. I'm using the random distribution, and I would like to go 2 outbound steps, plus I would like to apply a filter on the first level vertices that I find. So first level should have an age of 36. And if I execute this query, it takes a long time. And that is because start vertex is somewhere, its edges may be distributed somewhere across the cluster, their vertices are somewhere distributed across the cluster, their edges are somewhere in the cluster, and so on and so on. So I need lots and lots and lots of HTTP hops to actually query this, but at least it works. So in 4 seconds I can get friends of friends of one of those persons. And this is, as I told you, the price that I pay. If I use the random distribution, I get equal distribution, but slower queries. And then I have to talk about so-called index-free adjacency, which is the thing that most other graph databases do. So ArangoDB uses an edge index, which allows us to actually separate the edges from the vertices. But most other graph databases use index-free adjacency. That means they store the edges directly attached to the vertices. So every vertex maintains 2 lists, in and outbound edges, basically. But how to shard this? So in this example, I have a pretty simple graph. I can just put the left part on the left server, the right part on the right server. So now taking into account the overall layout of the graph to improve the locality of my algorithm. But the thing is, where do I store this edge? Is it left or is it right? Probably both, but then again the connected vertex is not located at the edge. So that is actually a problem. And as ArangoDB uses the hash-based edge index, which has constant time lookup, I can actually store the edge on the left-hand side or on the right-hand side, and the other one just has to request it somewhere. And now I would like to introduce something that we call domain-based distribution. Because many graphs actually have a natural distribution in their layout, what they have. And from all our clients, this natural distribution is known. So everyone who asks us and say, okay, we have this super large graph, and we want to store it in Arango, and we want to shard it, or we have to shard it, they can figure out, okay, there's one attribute that actually divides this graph pretty good into parts, subparts that are largely connected. So whenever you have people in the graph, it's typically a country or a region, because most of your friends will be from the same region, from the same country, and only some of them will be from far away. If you store blocks, typically the tags will be a good indicator, because typically blocks with the same tags are somehow related. If you store products, typically the category products are somehow related. And therefore, if you find this natural attribute that distributes the graph, most edges will stay in the same group, and just rare edges will be between groups. And if we take it into account and just distribute the same graph now on our 3 servers, we can somehow do it like this. So large part on the left, large part on the right, and not so large part in the middle. And here again we use the feature that ArangoDB uses in hash index, so we can actually store the edge here and do not have to replicate it to the other one. And ArangoDB only enterprise version uses this domain knowledge for shortcuts whenever querying the graph in a cluster. And now I would like to show it to you. So, going back to my cluster. As I told you, for collections 2 times the same dataset. Just to prove, 1.632.803 documents. Profile smart, same number, same documents. Same holds true for the relations, 3.5 million, and here again, 3.5 million. And now just execute the same query, but using a different distribution of the graph. So what I have to change is, now I start in the profiles smart collection, and I'm using the smart imported graph. Remember, 4 seconds to beat, and off we go, 100 milliseconds. And the result, ignoring the order, is exactly identical. And therefore, with using this domain-based distribution, you can actually speed up clustered graph queries a lot. And if you combine that with Vertex-centric indices, which I haven't done yet, get even lower than this number. And suddenly, a graph of substantial size can actually be handled. Just a couple more words. We did an open source benchmark because we wanted to compare to all the other vendors out there. And as I told you, OrangoDB is a multi-model database storing JSON documents, graphs, and key values. And therefore, we actually compared to the leaders in their field, MongoDB for document store, Neo4j for graph database, OrientDB as another multi-model competitor, and then we have Postgres, which is one of the more well-known relational databases. And we tried to execute some queries that are reasonable for a typical database load. And we just, as we started with this benchmark, we expected that we are a bit slower than all the other vendors because they have specialized for one specific use case and we have to cover 3 of them. But it turned out that we are actually not that bad. So in terms of single read, MongoDB is a bit ahead of us, but all the others are actually slower. Then we have single write and single write sync, which means we wait until everything is synced to disk, where we also have pretty good performance. And then we have aggregation, which is, I just want to aggregate all the users by their age. And we figured out that we are actually pretty good. And for MongoDB, Neo4j, MongoDB and Postgres. So Postgres is very, very good here, but only if you use the tabular way. So where you define the age is actually an integer, because they can make some optimization because they know it is an integer. For us, as a schema-free data store, we do not know that all our attributes have this age attribution, and we do not know that it is always an integer. So we cannot do these optimizations they can do. If you go to JSON, they're actually way slower. And when it comes to graphs, and this is just a single server version because Neo4j is not able to shard a graph, they always have to fit it on one machine. And we actually expected them to be closer to us, but well, they aren't. I don't know why, but they aren't. But as soon as you really include all the details of the data, it is overshadowed by the network latence. So whenever the engine is a bit faster, then the whole amount of data actually pays off. The price you pay in at least the released version is that we use a bit more memory than all the other vendors. We're gonna fix that with release 3.2, where we can just define an upper limit of memory and we will not ever cross that. But 3.2 is ongoing, it's not yet released. Good, thank you very much.